Welcome back, everybody. We're now talking about projectile motion. And projectile is when you're throwing something out. So you're throwing a ball, or you're shooting a cannon, or something like that, or shooting an arrow. Once it leaves your bow or your hand or your gun, the only thing that's pulling it is gravity. So something that's in projectile motion only has one force on it, and that's gravity. But it also has something that we've talked about before, and it has inertia. If you have a velocity in a certain direction, it will continue in the straight line in that direction unless acted upon by another force. So let's look at this picture. If this girl is throwing a ball off the top of a mountain and there's no gravity at all, then it's going to go in a straight line at a constant speed. And so you can see here that she's got equal distances between her ball. That's showing that in a certain amount of time, let's say that's 1 second, it'll be here, in another second it'll be here, and another second it'll be here, and so on. So it would go forever in that direction. However, as soon as the ball leaves her hand, it's under the influence of gravity. And so it's actually going to be traveling in two directions. It's going to be going forward at a constant speed, and it's going to be going downward at an accelerated speed. When you put those two together, you're going to get a typical parabolic shape, which is typical of throwing a ball. If you've ever shot a basketball or thrown a baseball, you know that it shoots in an arc. That arc is a parabola, and the parabola is a shape that has a constant x direction and an accelerated y direction. So that's what we're going to look at. So let's look over at the side. It says, the directions at the bottom says, use the scale of 1 centimeter, so they've got a centimeter ruler here, equals 5 meters, and draw the positions of the ball dropped at 1 second intervals. Neglect air drag and assume that G is 10. Estimate the number of seconds the ball is in the air. All right, so first of all, let's go and remind ourselves of what the distance formula is. D, if there's no initial velocity, if it's just dropped, you can simply ignore the first part, which is initial velocity times t. We can make that 0 because there's no initial velocity. And then the second part, if you remember, is plus 1/2 gt squared. Okay, g is acceleration of gravity, which is 10. It's 9.81 meters per second, so this is 10 meters per second. T is the square of the time, and then it's 1/2 of that. All right, so let's just put in the time because we're doing at 1 second intervals, and let's just do a grid here at the side. If you put 1 second in for time, 1 times 1 is 1, and then 1/2 of 10 is 5. So let's rewrite that as 5t squared, just make it easier. D equals 5t squared. And now let's do the grid. 1 times 1 is 1 times 5, so at 1 second it's going to fall 5 meters. Okay, now let's do 2 seconds. 2 times 2 is 4, times 5 is 20. So at 2 seconds, it's going to have fallen 20 meters. Okay, so it only falls 5 in the first second, but it falls 20 in the second. 3 times 3 is 9, times 5 is 45. In second 3, it falls 45 meters in second 3, total. In second 4, this is 4 times 4 is 16, times 5 is 80 meters, and we've run out of room. So that's all we're going to have. Now we're going to use 1 centimeter equals 5. So let's do this one first, okay, along the side. At 1, it's going to drop 5 meters, so we're going to go 1 centimeter, okay, in 1 second. So it hasn't fallen very far from the girl's hand, okay. Now what? It's going to fall 20. Now it's 20 total. In the first 2 seconds, it will travel 20 total. So it's not going to be 20 from where the ball is after the first second. It's 20 from the hand. All right. In the first 2 seconds, it's going to travel 20. In the first 3 seconds, it's going to travel 45, and then the first 4 seconds, it's going to travel 80. So we're going to now go down to 5, 10, 15, 20. Okay. So that means we're going to go 4 centimeters down, and that's the same as 20 meters in the scale. The next one is 45. So it's 5, 10, 15, 20, 25, 30, 35, 40, 45. So we're at 9. Right? The last one is 80. So it's 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80. It hits the ground. So let's go ahead and answer the question. How long does it take to hit the ground? Well, it's traveled 1 second, and here it is after 2 seconds, here it is after 3 seconds, and here's that after 4 seconds. It's going to take 4 seconds to hit the ground. Now, what you're going to see in this, and I really like this page a lot, it's showing you that in the x direction, this is x direction here, and this is y direction here. In the x direction, it's going to be constant motion, non-accelerated motion, equal times and equal distances. In the y direction, it's accelerated motion because of gravity, and so you're going to get longer and longer and longer distances as you go. Okay? So what we're going to do is we're going to simply form a grid. If I go straight down from here at 1 centimeter, that's where the ball is after 1 second. If I do the same thing and grid it over here and go straight under this ball, this is where the ball is after 2 seconds. And you can already start to see the arc. If I go straight under this ball, but I go straight over from this, okay, you're going to get the 3rd second, and then the 4th second is straight under this ball at the ground. Okay, so it's going to be here. So your arc is going to be a parabola, a parabolic shape, which is going to show you it's never a straight line, it's always a curve, but it's not just a curve, it's a parabola. A parabola is constant on the x and accelerated in the y, and that's what that is. Love that. Okay, so let's look at the last question on this page. Draw the 4 positions of the ball shown with no gravity. That's what it is, no gravity at 1 second intervals. And then at 1 equals 5, carefully draw the positions with gravity. So here's with gravity, here's without gravity. And so you're going to see that it's still traveled this far in 1 second because it is inertia just says constant speed in one direction unless acted upon by another force. So if there was no gravity, it would go on forever, but since there's gravity, it's pulling it in 2 directions. It's moving in the x direction and moving in the y direction at the same time, eventually hits the ground and stops. Okay. So the question is, how is the motion of the vertical direction affected by the motion of the horizontal direction? Okay. Well, if you remember from yesterday, the x and the y components of vectors are unrelated at all. They are completely independent of each other. So I would just say they're independent. So the fact that it's falling has nothing to do with the fact that it's moving forward. If I didn't have any moving forward, it would fall at the same rate and at the same speed as it did when I had an initial velocity. It's just going to go farther out before it hits. And it's going to go out at certain intervals, but it's going to hit at the same amount of time. So this is the idea that if you shoot a cannonball and drop a cannonball, they'll still hit the ground at the same time because they're independent of each other. Okay. Now this one adds a little bit of an interesting thing. You're going to have an initial velocity down. So some of his force is going straight out, some of his force is going down. Okay, so if you remember, if this is the resultant vector, okay, what he's throwing, some of that, if you make a parallelogram, some of that is a straight outward force, and some of it is a straight downward force. And if you remember, we made a parallelogram to show that vector. So here's the direction he's throwing it in, and the inertia, first law of motion, said that this will travel in a straight line at a constant speed unless acted upon by another force. Okay, so we're going to see that after 1 second, it's the same. It would travel at 5 meters. So we want to go, yeah, that's bad, isn't it? the ball is, well, I guess the ball is here. Okay, we want to go down 5 meters in 1 second, and then 20, and then 45, and then 80, the same as we did before. So what are we going to do? That's what it's asking here. The time the ball is thrown below the horizontal. Use the scale 1 centimeter to 5 and carefully draw the position of the ball falls beneath the dotted dashed line. Connect your positions with a smooth curve. Estimate the number of seconds the ball remains in the air. All right, so we're going to see that the first one is dropping 5 meters. Okay, so here's where it is, but gravity is making it drop 5 meters. So right now it's at 1, but I want to go below 1 5 meters. So I'm going to go 1 centimeter below. So this, sorry about that. I'm going to go one centimeter below, that's 5 meters. And now I'm going to go, what? 4 centimeters, because I want to go 20 below this one. Okay, so here is this one. I want to go 1, 2, 3, 4. So I want to go down to the 6. That's the second one. The third one is 45. Okay, 45. I have to keep counting. Somewhere like that. Okay. And the fourth one, I want to go 80, but I don't have 80. So the fourth one would be way down below the picture somewhere. Okay. Probably somewhere, I don't know, around here maybe, would be 80. So it's actually going to fall before the 4th second. So if you're throwing it down, if you're throwing it straight out, it would fall in 4 seconds. But if you're throwing it down it's going to be less than 4 seconds that it hits the ground, because some of that speed is coming from your arm, not just from gravity. Okay, so it's going to be looking like something like this. So it's going to hit somewhere here, the ground. This would be the place of impact of the ground. So how would I find out the time? Okay, so, well, let's just estimate. Do you see here is 3 seconds, here is 4 seconds. What's the estimated time here? Can you see that it's roughly half? I would say it's going to be in the air 3.5 seconds. Just a guess. It might be 3.4 seconds or 3.35 seconds or something, but it's about in the middle between 3 and 4, so I would just roughly guess 3.5 seconds. Okay. Here's the last question. Suppose that you are an accident investigator and you're asked to figure out whether the car was speeding before it crashed through the rail of the bridge and into the mud bank. Poor car is in the mud bank right here, stuck in the mud. The speed limit of the bridge was 55 miles an hour, which is 24 meters per second. What is your conclusion? Okay, so I want to know, he's dropped 5 meters. Okay, he's dropped 5 meters. So it's taken 1 second to fall, and he's gone 24 meters in 1 second. Okay, so he's gone 24 meters in 1 second. So the speed limit is 24 meters per second. So he was going 24 meters per second here if he was going 55 miles an hour. It takes him 1 second to fall, because every second you're going to drop 5 meters. Okay, in 1 second. That's what we saw before. 5t squared. So 1 times 1 is the time times 5. So he's going to drop 5 meters in 1 second and 24 meters in this second. Now, did he drop an entire second? Okay. How much do you drop in a second if d equals 5t squared? 1 times 1 is 1 times 5. He should have dropped in 1 second 5 meters. Did he drop 5 meters in 1 second? No, he only dropped 4.5 meters. So actually it took less than a second for him to fall 4.5 meters, but he traveled a full 24 meters in that time that was less than a second. So if 24 meters in 1 second is the speed limit, and he dropped 4.9 meters, not 5, in less than a second, but yet he traveled 24 in less than a second. Then he traveled 24 meters in less than 1 second, which means he was going more than 24 meters per second. So he was speeding. I would book him, Dano. Okay, I hope this helps you, and I'll see you in class.